Sorry for the technical difficulties. So gonna introduce our Midas expert today. Like a lot of the other Midas experts, Amir has lots of experience in the field of civil engineering with special emphasis on concrete structures and bridges. He is a senior bridge engineer from SDR Engineering. And he has, all these achievements that's shown on the screen. And I think it will be better if Amir, you can introduce yourself.
All right. So yeah. So my name is Amir Botros, and I am from Egypt. I got here to the United States in 2012 to get my PhD from North Carolina State University, and my PhD was mostly in precast, pre-stressed concrete, and it was specialized in the beams with the dabbed ends, how to address the reinforcement details for the beams with the dabbed ends. And we had a nice project with the PCI, the Pre-Stressed Concrete Institute, that resulted in some good design recommendations that were included in the PCI Design Handbook in the 8th edition. After that, after finishing school and graduating, I moved to SDR Engineering Consultants, and this is because I enjoyed working in bridges since graduation with my bachelor degree. So I was looking to work in a firm that is specialized in designing bridges and load rating, definitely. And that's where I am right now. And in 2018, I got the TY Len Award, and this was as some sort of acknowledgement to the design recommendations that, or the guidelines that were included in the PCI Design Handbook that were coming as an outcome from my PhD research. I'm happy to be here today with Midas Group and to talk about the topic of the construction stages. I know how important and crucial this topic is in bridge engineering, and that's why I'm enjoying today to be with you for this time and talk about some nice features in the construction staged analysis. Yes. So you like me to start with answering the questions?
For your introduction, and I want to thank everyone again to come. And so before we begin, I want to lay out some of the ground rules for this discussion. So of course, we do encourage discussion because it's a Q&A session, but I just want people to know that when there's one person speaking, you should mute yourself. And if your question, because this Q&A session is only 1 hour, and we understand your question might not be answered in great detail, but do not worry. Me and some of my Midas colleagues, we will stay after this discussion session. If you do have any questions regarding the software, we're glad to answer that. So yeah, I think we can begin with questions. Amir, I think you have the slide as well. Do you want to just, I can make you the presenter.
Yeah.
And
yes, yeah. Please. That will be great.
Right. I think you can share your screen now.
Okay, so you can see my screen now?
Yes.
Okay. All right, thank you. So I have seen some questions that first of all, I thank all of you for coming today and putting this time in to discuss this topic. And I have seen some interesting questions regarding the staged construction analysis. And that's why I wanted to share my screen to just discuss some things also on Midas to show you or to emphasize the importance of having the construction staged analysis in different types of bridges with different degrees and levels of complexity. So the first question that I came across is this one here, how to define construction staged analysis in Midas Civil and any difference compared to CSI bridge. Of course, that's a big question by itself because it's not easy for me to go on every single detail about how to define the construction staged analysis, but I can give you an overview how Midas works in terms of defining the construction staged analysis for 3 different types of bridges of different degrees of complexity. And how does this compare to CSI bridge? I honestly worked on the CSI bridge on the last version that I worked on was CSI bridge 16. The one that came out in 2016, and I can see that there are really a lot of differences between how Midas introduces the construction staged analysis in a simple way, and the CSI bridge is a little bit cumbersome. I don't know why. The module that's dedicated for the construction staged analysis, the way when I started working on it, I found it a little unfriendly in terms of activating elements or deactivating elements or boundary conditions or for example different loads. Also, after running the analysis with the CSI bridge, I found some issues with the deformed shape of the structure at different stages. It was not really matching what we think is the logic thing. So I had some issues in CSI bridge. I kept also contacting the team for CSI bridge for help, and they are really very cooperative and they respond to questions very quickly and answers. But when I came up to solve the issues with them one by one, the issues that I faced in my model, I found that it is really somehow related to how you introduce your program and the interface. If they have done some more enhancements on the module that is dedicated for the construction staged analysis, I would not have run through all those difficulties. So just to talk quickly about staged analysis, just to give you an idea or overview about Midas. So basically Midas, like any other finite element software, you have all the basic modules that you need to define your materials for your structure. I'm here talking, this is the first example that I'm just showing very quickly for a simply supported precast, pre-stressed concrete girder bridge. So this is something that we all meet every day. It's a very common bridge types that we are modeling every day. This is just single span, simply supported at the 2 ends, and I just want to introduce to you very simply how Midas introduces the construction stages. So first of all, you have to input all the inputs related to material, section definition, like any other software. Of course, use beam elements or use shell elements or plate elements, whatever the type of elements that you use to define your girders and your deck on top of it, and also define the different static load cases, including the self-weight, the deck weight, the barrier weight, the pre-stressing tendons, everything like any other software. And then you come up to the construction staged analysis. So this window here is the start for the construction staged analysis, and you need to define how many stages you need to apply for your model or for your structure. So we all know that for any precast, pre-stressed girder bridge, we have a stage when we have the girders placed on top of the piers by themselves, the precast, pre-stressed girders this way. So this can be the first stage. And then you go to a second stage here where I applied the pre-stressing tendons or the pre-stressing strands to those girders here. So this is the second stage of the pre-stressing. And then you come to a stage when you are pouring your concrete deck on top of that. And we have to pay attention at this stage that basically the element that is resisting the weight of the fresh concrete or the concrete that's poured on top is basically the girder only by itself. So the stiffness that is really effective in this stage is the stiffness of the precast, pre-stressed girder only. And that's why when you apply this deck weight, you have to apply it in the form of uniform load or uniform distributed load on top of the girders. Then you have a stage when you activate the composite action. And what I mean here by activating the composite action is basically you have the deck here now start to be activated in the model in the form of stiffness, like the deck starts to harden and it becomes composite with the girder. So this is where your stiffness starts to be the composite section stiffness. The deck and the girder are working all together. So this stage, I call it composite girder. And then after this stage, you have all your loads that come after activation of the composite action, including the barrier weight, for example, which is uniform distributed load that's applied on the at the barrier location here at the two sides of the roadway, and then you can later on apply the live load or the moving load analysis or whatever, anything that applies post-construction stages. So the way this works for anyone who's not familiar with Midas, usually in any construction stage, you have three different options. And those options, you can either activate an element or deactivate an element. Element means you have a beam element or a frame element or a plate element, any type of element that represents an element inside the bridge. Is it a main girder? Is it a diaphragm? Is it a shell or a deck on top of the bridge? Whatever it is. So you can activate the element or deactivate the element. And also you have a boundary condition. You can activate a boundary condition or deactivate a boundary condition, which means your support condition. And the third thing that you can activate it or deactivate it is the load. And the load also is not only dedicated for the uniform loads that are applied or the concentrated loads that are applied. You can also activate a wind load if you want to. You can activate pre-stressing load, because the pre-stressing is defined inside Midas as a load, of course, the tendon load. It's a load that's applied to the girder at the end of the day. So you can activate or deactivate any one of those three: element, boundary condition, load. So if we go again on our stages, this stage number 1, where I have the girders on, you will see here I defined all the girders in one group that I called it main girders, and I'm activating this main girder. So if you go to this stage here and display, you will see only the frame elements that represent the beams here or the girders are activated. Of course, we cannot leave the beam elements in the air without being supported. That's why you will see I have some some nodes down here. I have some elastic links that are connected between those nodes and those nodes that represent the depth, the solid depth of the girder. And also I have to have some supports that are defined in there. So that's why here in this stage, you will see that I, beside activating the main girders, I have activated the support condition, which are those rigid links, the vertical links shown here, and also the bearings at the two ends of the bridge, at the two ends of the span, the start of the span and the end of the span. All of those have to be activated. Otherwise, Midas does not understand that this structure is stable. It has to have supports, of course, activated from the very beginning. And in terms of loads, I just activated the self-weight load case, which automatically Midas calculates all the dead loads of the structure or the self-weight of the girders and apply it right away. So whenever this stage comes into operation, Midas understands now that we have the beams. The beams are supported at this ends, and it has the self-weight of the beam applied to the girder. When you go to stage number 2, the pre-stressing, you will find in the pre-stressing, I just activated the tendons only, or the pre-stressing strands here. So if you go here, you will see here no elements are added in this stage. No boundary conditions are added. I just activated the pre-stressing effect only. So now I'm having the pre-stressing also counted for inside the model. If you go to the next stage, which is the deck weight, you will see no elements are added yet. The boundary conditions are the same. No boundary conditions are modified in this stage. And the last thing, I just applied the deck weight. And because the weight of the fresh concrete and the diaphragms that are still fresh, all of this weight is going only to the pre-stressed girders. That's why I applied here the weight of the deck as uniformly distributed load on top of the girders. And you can see now Midas fully understand that this load is being resisted by the stiffness of the girder only, not the composite section. And that's why this is a key important thing in the construction staged analysis, that it mimics exactly how your structure is constructed. And whenever a load like this is only supported by the beam or resisted by the stiffness of the beam, is going to be captured by the construction staged analysis. But this cannot be captured in a model without construction stages. Then going to the fourth stage, which I call it composite girder, this is where I activated the deck elements. And the deck elements, I presented them here using grillage elements or beam elements as well. Somebody else can use plate elements for the deck. That's totally fine. It's totally okay. And you just activate those elements in here. So now At this point, the structure is going to activate the stiffness of the deck, and now the deck and the beam are in composite action together. So the full composite action is going to be activated at this point. And that's why when you look at this stage here, you will see I activated new elements in, which are the cross elements that represent the deck. I have the intermediate diaphragm, I have the end diaphragms of the span. All of those are activated here. No boundary conditions activated, no loads are activated. This is also very important, by the way. When I activated all those deck elements and intermediate diaphragms, you have to make sure that those elements are not having any weight that is applied to the girders, because you have already applied the weight of the deck as fresh concrete here in this stage. Remember, we applied the load here as uniform distributed load on the girders. So do not apply it again in the composite girder, otherwise this load is going to be duplicated inside your structure. So to do that, you want to make sure that those elements, which are the deck elements here, are having or using a material that is, this is one of the ways to do it, of course, that you can use a material that's called dummy concrete. And this means that this material doesn't have a weight. So this way, when those elements are activated, they are activated only in terms of stiffness, but not in terms of weight. And finally, after crossing this stage, we come to the last stage, which is the barrier one. And here I'm just applying the barrier weight, which comes after the whole structure, of course, is casted. It's just casted on top of the deck. Of course, any other load case you can apply after that, the moving load cases, your live load, either you choose to apply static load or definitely use the moving load analysis, which is a very powerful feature here by Midas. All of those always come post-construction staged analysis. Also, the beautiful thing here in Midas that you can see when you define the composite sections. I have here the composite sections defined. You will see that Midas gives you the option that you define for the beam element. You can define the girder as part number 1 and the deck as part number 2. And also you have the liability here to basically say that part number 1 is activated in the first stage only, which means when the girders are only applied on the bridge, this is only part number 1 that's active, and then parts 2 kicks in stage number 4 when the bridge becomes in the composite stage. So this way you fully guarantee that the deck stiffness is going to be added to the beam stiffness, and the composite action is going to be effective right at this stage, not at the beginning or the first stage. So this example, I'm sorry, it just took some time in it, but that's a very basic example that shows you how Midas handles the construction stages. It is basically you define whatever number of stages you want to, and you either activate or deactivate an element, a boundary condition, or a load. And that's how you can mimic exactly the response of the structure based on the construction stages or how it is constructed. So some of those features, going back to your question, some of those features are not really reflected nicely and clearly in the CSI bridge. For some reason, for example, I'm going to mention to you one thing that I came across is the application of the load. If you apply a load activated or deactivated, this is not how it's presented inside CSI. So for some reason, you can activate a load, but you don't have a way to deactivate the load. And I contacted the staff over there, the technical staff, and I was shocked actually when they told me the only way to remove the load is to apply a load in the opposite direction. So you can imagine, for example, if you are applying concentrated load in one location and then you go again and define another load case that you apply the same concentrated load but against the gravity direction. So this way you are taking out the original load. So that's only one aspect, but I have gone over other things with them also in the deformed shape and some other issues that I don't think that we have enough time to go over the whole thing right now, but that's only to show you how we deal with the construction stages with the two softwares. Also going into, before leaving your question, construction staged analysis becomes very important when you have more complex bridge. For example, this bridge here was a steel I-beam continuous girder bridge, and this bridge consisted of two girders here. You can see those are two girders, and they are connected using some floor beams, and you have the deck cast on top of that. And this bridge is crossing. This is one of the projects that I worked on here, and this bridge is crossing the I-10, and this particular span was crossing the I-10 here, and it got hit. The girder got hit with the truck. The truck, you know, this issue, we all the time come across this issue in the United States. Trucks hit the girders here, and the girder was damaged, and they asked us or requested us to take out the portion of the girder that was damaged and replace it. And you can imagine, if you have a bridge that is supported on 2 girders only, and you are taking one of the main supporting elements out. So this is not a redundant system. It has only 2 supports. So it's a very critical thing for the construction stages. Plus, the bridge is a continuous. You can see this is a continuous girder on 4 spans, like you can see here. So this statical system is not an easy statical system to deal with because of indeterminacy, and you have to expect what deformations you will get while taking out the girder and putting the new girder in. So this is another degree or level of complexity. And to do this, I defined all the material sections, all the static load cases, and came to define the basic construction stages here. So we have a case, I had a case when I have the bridge in service. This is the bridge under service. So I'm defining here all the girders, all the floor beams, the deck, everything, and the piers and the columns, everything for the bridge and all the supports. This is the bridge under service condition with the barrier load and everything. And then we came to another stage where I had to define temporary supports here, because we are now going to remove part of the span here. So when you take out this part, you are leaving an overhanging portion of the girder here and an overhanging portion of the girder here. So when you take out the load, this overhang is going to move upward. The deflection here is going to be upward. And because this is a continuous bridge, you expect that those points are going downward to maintain the same rotation at the support. So in order to overcome this upward deflection thing, we had to apply temporary supports or shores right at these locations. And also it was very tricky to decide the locations of those temporary supports, because this is crossing the I-10 and you want to make sure the lanes under the I-10 are fully in operation during the construction of this or the replacement of these girders. So I had to apply temporary supports here. And span removal stage, where I came and took out the deck elements first, and then took out the floor beams that are under the deck, which are the cross beams in this transverse direction, and then take out all the steel girder elements that need to be replaced. So now you see how we transferred from a statical system of a 4-span continuous bridge to 2 pieces here. You have a span and overhang, you have 2 spans and an overhang. That's completely different. You cannot predict what type of deflections easily without having a construction staged analysis deployed in your model. So this is stage number 3, span removal. And stage number 4 was adding concentrated loads in the form of counterweights that we had to add at those 2 points here because of the upward deflection that we got after removal of the span. So now you are adding loads to make sure those 2 points are down again. So when we come and install the new girders in, those 2 tips are on the same level. So you have to decide how much load you need at each one of those 4 nodes, and they are unequal because this geometry is curved geometry, and the span, the overhang length here is different from here. So that's a kind of construction that is really tricky and has to deploy the construction stage analysis to do it. And the interesting thing about this project, that after we did it, the deflection that we upward, or the deflection that we estimated right at those points under the counterweights was within 2% difference from the deflection that they measured in the field. So that was really very interesting. The third level of complexity, and I'm not going to talk about this much. I know that this is a very complicated thing, but I'm just showing you how construction staged analysis is employed in different levels of complexity in bridges. So I had the opportunity also to work on a model for a cable stayed bridge in India. And you can see for those types of models that you are going over the construction segment by segment. It's a segmental construction, and you are applying each segment and each stay in a construction staged analysis. You also have to account for all the loads that are coming from the derrick or the gantry that's on the very tip of the structure that picks up a segment from the water all the way up, install it in, pre-stress it, and then you apply the state to support it. So you can imagine a model like this, how much construction staged analysis is very important, especially for the dead loads and other loads that you can never estimate by hand calculation or by any other way the deflections, unless you use finite element and construction staged analysis. This model, for example, you can see the construction stages were 52 stages, different stages. You can see how many static load cases you have to define in a case like this to account for all the loads on the structure, including erection loads, steric loads, or gantry loads, or also jacks. Pre-stressing effect has to be counted for, self-weight, and the pre-stressing effect and everything. So this is just trying to get you an idea about this staged analysis, how it's introduced in Midas and how much different it could be from CSI bridge. Hope this answered your question. So moving to the second question here, I had a question that how to tackle or imply the dead load effect, especially when getting large deflection during construction stages. I'm not sure about this wording here, tackle or imply, is this, your question is basically about when you define or when you encounter during the construction staged analysis of the structure large effect or large deformations from the dead load, how we can overcome this dead load effect?
So I think Kodama was asking about like when she was using the dead load
Yes.
during construction stage, she was getting a very large deflection, and they're
Yes.
not sure if this is correct. But I think Kodama is also here. You can, if you don't mind, briefly explain your question a little bit, if you can unmute yourself.
Hello, everybody. Yes, actually, I already did a long span bridge, and when I did the analysis, shows me like high deflections, which is when I check the live load, like services or the deflections due to the live load was checked, was okay, but the dead load, because we have steel structure like a long span, like high depth girder, it shows like a very significant high deflection or from the web. So I was when I checked out, like sometimes the dead load during the constructions, I mean when you do the construction, the dead load causing the high deflection, but somehow we during the construction we can avoid that. So because the live load it's checked, I mean it's with the L over 800 for AASHTO, I got 0.4 feet, which is I got like about 4-inch deflection due to the live load, but with the dead load I got about 10 inches effect when I check the result.
Yes, so if as far as I understood your question, just to be accurate in answering this question, tackling or implying the dead load effect, we have to know first what's the type of bridge that you are talking about, because there are various methods of doing this. Definitely, any bridge under live load, you have a limit that you check in the code, like L over 800 or whatever, depending on the case of the bridge. And this is designed because the live load is in and out all the time. So that's why you expect to have deflection from the live load, and you just limit it to the code limitation. And that's how you design your bridge. But for the dead load, this basically depends on the type of the bridge. For example, if I'm talking about a bridge, a box girder bridge that is done using segmental construction, like the balanced cantilever method or something, you have at some situation you cast your pier and you have your segments that are overhanging from both sides of the pier. So this is a double cantilever thing, and this is a completely different statical system than the final condition or the final stage of the bridge, when the bridge becomes continuous all the way. So in order, of course, definitely you get different dead load deflections at this stage, and they are quite significant. So the way that you tackle this is during construction. When they do this, they apply camber, or they have a way to camber all this amount of dead load up using jacks, using hydraulic jacks. They can have temporary shores and put jacks on top and apply this in order to overcome the dead load effect, because the dead load effect, you always have to design your bridge during construction stages to have this camber effect in, or to overcome the dead load deflection. So that's, for example, for a segmental bridge, but that's not usually the case. It depends on the type of the bridge that we are talking about and how to address this issue.
Yeah, I'm using composite steel bridge on the about 325 feet. The span is 325 feet, the mid span. Yeah, I'm using composite steel. Yeah, but
usually,
you are right.
You will have temporary shores, you will have temporary supports inside, you will have jacks, you will have ways to control the dead load deflection that's coming during construction stages until you connect your closure segment or finalize the span construction, whatever the way this bridge is constructed, and that's how you start dealing with the final stage.
Yeah. So this will lead for another question. If you have time, I can ask because this is can I ask questions?
I have 6 more questions to answer from your colleagues, but definitely, if you want to send me your question written or something after that, I can discuss more.
Yeah. Okay. No problem. It's just because it's related. It's okay. I will send it to you another questions and then we.
All right.
Yeah.
Sure.
Thank you so much.
You are welcome. So question number 3, I got this question from Carlos, and he said, I need to check a bridge erection during wind during construction. And then he defined 2 different cases: construction inactive, construction active. So he was talking about applying the wind load whenever the construction is inactive, like you only have few elements of the bridge that are erected or installed, but you are not doing any construction, like not pouring the deck or adding more elements or something. So if this case may be more critical for the analysis when you apply the wind, or when you have the case when you are, for example, casting the deck, and during that he wants to apply or combine this with the wind analysis. So I'm going to talk to you about applying the wind load during construction analysis in general, without tying the answer to an active condition or an inactive condition. So this is basically the best way that I used in the past to check those wind loads, is to use static loads for the wind loads. It is not really easy to combine dynamic analysis or any kind of dynamic load or something during the construction stages. This becomes very cumbersome and very misleading. And sometimes also, I think also Midas does not allow you to use this combination of moving load analysis, for example, with the construction stages, or dynamic load. This cannot happen. So the best way is to evaluate your wind load that's going to be applied on the structure and apply it with the simplest possible configuration in the form of nodal loads or uniformly distributed load on the exterior girder, or whenever, if you want to distribute it on multiple girders based on the bracing condition or the diaphragms that you have in your structure, you can go ahead and always apply it using a static load. And in terms of combining this with an active condition or inactive condition, the way you can simulate this inside Midas is simply when I showed you guys for this, for example, for this particular span here, I can define a load case when I apply the deck weight. So this case, I'm applying the fresh weight, the weight of the fresh concrete on top of the girders. If you want, you can also combine inside this stage the wind load if you want to. If you want to address this case of having an active condition on your structure. So within the same static case, when you apply the dead load as a uniform load on top, there is nothing that can stop you to apply those nodal loads on the transverse direction or a uniformly distributed load on the transverse direction. And this way you are combining the wind effect together with casting the concrete. Or if you want to apply it for an inactive case, this means that you can always create a separate load case and call it wind on the during erection or wind during construction or whatever, and you can just apply the load on the elements that are active in this stage in the configuration that you see, and you can go from there. So you can applied as a stage by itself if you don't want to combine it with any other construction activity that's going on, or you can combine it in any construction stage that you want to. So, so we can move maybe to question number 4. This is from Chirag, and she's asking, how can we apply lateral loads, static wind and earthquake load in construction sequence analysis, and can we do dynamic analysis with construction sequence? Is it possible to apply the response spectrum in construction sequence? That's why I just talked about this in the previous point. Never attempt to combine dynamic analysis with construction sequence analysis or response spectrum. To me, this is too much complication for the construction sequence analysis. And usually those cases, like the response spectrum for earthquake loads, usually this is a post-construction stage analysis. That's from my point of view. I usually do this in working in my bridges. So something that's also similar to this, when you apply moving load analysis, this one, just to apply your trucks or your vehicles, and you define the lanes and you run the vehicles on the lanes. This is never combined inside the construction stage. You cannot combine moving load analysis with construction stages. This is usually applied as a post-construction stage. After the construction stages, you apply your live load, which makes sense because the live load will never be applied until the bridge is open to traffic, which means it's 100% constructed. So the same thing also, if you want to employ the response spectrum or dynamic analysis, this has to be out after the construction stage definition. Definitely applying the wind or the earthquake during the construction, because this is an important check that you want to check your structure under dead load only and static load. I would recommend usually to do this using static loads. So you can evaluate the wind load on your structure and basically apply it in the simple way, like concentrated nodal loads at particular nodes in the structure, or uniformly distributed load on particular elements of the structure, whatever you want, or the earthquake load can be treated in the same manner. Question number 5. So people like the wind load during construction. I think this is a very popular topic, and he's saying how to apply it and design for it. So applying it is, the way I do it for myself is basically applying it using static loads as in a separate construction stage, and it can be applied whenever you can run different trials. Like, for example, apply the wind when, for example, for this particular model that I was talking about here, we can have a stage. For example, after the placement of the girders with the pre-stressing, apply the wind load here and check if this is okay or not for the girders, and then you can pour the deck and then apply another case when you apply your wind load and check now when you have your deck and casted already and you have your composite bridge, how does it respond under the wind load effect. So I will not call it designing. We are really not, we do not design on wind during construction unless if this is a very specialized bridge, when one of the complex bridges that the wind analysis is very critical for them, the long span ones, the complex ones, like the, I can say segmental ones, cable stay ones, the long ones where the wind analysis becomes very crucial during construction stages and you have to check it. But we always call this a check. So I'm just checking my elements of the bridge that during construction, if the wind load is applied, they still have enough or maintain enough capacity, and we do not, for example, have tension reaction at one of the bearings or something that cannot be carried by the bearing, and we have to have some shoring, or we have to have some additional elements that should be applied during the construction to make sure that support the structure properly and the load is transferred to those elements away from the structure. So it is very important and crucial to check this kind of load, the wind during construction sequence, especially for the steel bridges. and you want to make sure that your bracing, all your lateral bracing or diaphragms that you apply are adequate for this particular load cases. Those diaphragms are more critical for the wind load during construction, even more critical than after the bridge is fully constructed. So that's the way. If I'm going to apply it, I will apply it in the form of nodal loads or uniform distributed loads, and I'm going just to check the capacity of the members and check that all the support conditions are fine and you don't have any tension on any of the bearings, and that the elements can carry the forces safely. Otherwise, you can start looking into adding temporary shores or other towers or elements that can help support your structure during the construction stage under a wind or so. Question number 6 here, we would like to know whether this is in any limitation, there is any limitation on the number of load cases to be distinguished from dead load for construction stage output in construction stage analysis control data. Our tests indicated that it is constrained at 3 load cases. So I will answer this. I will say yes, they are constrained to 3 load cases. And maybe this is a good question for Midas technical staff, so they can mention to us why they have this kind of constrain it to 3 load cases. But I have ran through this issue while doing this cable stayed bridge here, and you can see here construction.
Yeah, Amir, sorry,
yes.
if you don't mind me interrupting. We recently increased the number of load cases to 10.
Oh yeah, that's really good news, great news for me.
Yeah, so yeah, earlier when we first implemented this feature, so everyone can define their dead load, but to be able to kind of specify the dead load type for construction stage analysis, users had to kind of define their dead load type one more time over here, and the number of cases was limited to 3. But I think it's been about I think from early this year it's been increased to 10. So I hope no one actually runs into that issue anymore. But yeah, try the latest versions and let me know if you can. Yeah, if you can still not able to do it, but you should be able to.
Well, I'm going to try it on this particular model right here. And
yeah.
I ran through this. Thank you, Angela, for this information. So for all of you guys who may not be aware with this issue, so this happens usually when you do the construction staged analysis in Midas. If you, for example, activate some elements inside the stage, and you are activating the self-weight load case, this means that all those elements, once they are active, the self-weight or the own weight of those elements will be applied right away to them. And for some reason, we had other load cases that, for example, if I'm applying the pre-stressing effect together to an element, I'm applying tendons or cables to the element, and also I have the element activated with the tendons on the cables, and also it is activated with its self-weight at the same time. So when you display the results, in the past, we used to see in the construction stages, when we display the results, we used to see the results for both the dead load effect and the pre-stressing effect together in the same, or the dead load effect with the erection load or a pre-tension load or something like this. So in order to distinguish the results, to see the dead load effect away and distinguish the other load cases, like a pre-tension load case or pre-stressing load case or whatever, any load case that we want to distinguish from the dead load, you have to define those cases clearly here in this box. You have to say that we want to distinguish the pre-tension load case from the dead load, or we want to distinguish the weight of the gantry or the weight of the derrick that's on top of the bridge. The derrick or the gantry is basically the crane that lifts the segment and have this segment connected to the other one. So this gantry has a concentrated load that's applied on top of the bridge. So you don't want to mix the effects that are coming from this load together with the dead load of the element on the bridge itself. So we had to define those cases here. And in the previous years, those were limited to only 3 cases. But now, according to Angela, she said that they have increased the cases here up to 10. And I can see clearly the cases are increased. So you can add as many cases as you need and distinguish them from the dead load. Okay, that's good. Going to question number 7.
Actually, sorry to interrupt. So regarding Kodama's question before, I think he was running to like a very large deflection. I wonder if Kodama has tried to use the load cases to be distinguished from dead load case, because a lot of times results of other load cases are defined as construction stage type, except for creep, shrinkage, and relaxation of tendons. They're lumped into the construction stage. So yeah, like he can definitely try to select certain load cases to be distinguished from the dead load. Yeah.
Definitely, I agree. This is something that needs to be revised by him and see exactly what load cases are included or combined with this dead load case. Are you seeing the results from dead load only, or you are seeing the results from dead load and, for example, long-term effects, creep, shrinkage, or any pretension load that's applied, or erection loads, or whatever. So this way you can figure out why you are coming up with those large values for the deflections under dead load. So going to question number 7, this one here, I think we have 5 more minutes, so we are on time almost. I have found that the beam bending stress results are not correct for cross sections that are not doubly symmetric. The program does not realize that the section moduli can vary between corner points 1, 2, 3, and 4. Have you run across this? So honestly, I've not ran across this before, because many of those girders that we use in bridges, many of them are doubly symmetric. But the other thing that maybe can apply for this case, when you are using a U girder section, for example, for the bridges that utilize the LU girder shape as a pre-tensioned, pre-stressed concrete girder for the bridge, this U girder shape is a singly symmetric section. So I'll be interested if I display the stresses on the section and see that the 4 points, for example, it is indicating the same stress. It does not recognize the point that the section modulus differs between the 4 corners. But I have not checked that myself, Thomas, but this will be interesting to me to check it with while utilizing one of the girder sections that is a singly symmetric section. Or something. And what Thomas is talking about is basically here for other people can follow. So for example, if I run this model here, Midas gives you an option to see the stresses on the section, and this applies beautifully for steel sections and for pre-stressed sections that are operating with the full inertia or the full stiffness of the section, because they are fully pre-tensioned or fully pre-stressed. So which means that we are not dealing with the cracked section, we are dealing with the full section stiffness. So Midas usually gives you the option of displaying the stresses on the section, and it defines 4 corners of the sections, 1, 2, 3, and 4. I'm going to show you this shortly, but I'm just waiting for this to run. And you can see the stresses right away. So that's a nice feature in Midas. But it's going to be interesting to me if I just try one of those spans here, and that's utilizing a singly symmetric section or something, and I will check it myself to see the variation of the stress on the 4 points. You can always double check it by your hand if you, under a dead load case or only the self weight of the girder, if you can just calculate it by hand at the 4 corners, calculate the stress M over I times Y, and just check it versus what we get from Midas. So usually you can see the stresses here. For example, if I check beam stresses, this gives you the beam stress under self-weight. Let's say this is the self-weight of the girder, which is WL square over 8, as simple as WL square over 8. So that's what I'm talking about. You can show any component of stress that you are interested in at any of those points, 1, 2, 3, or 4, the 4 corners of the section. So that's what he is talking about in his question. He was talking that he had a section that is singly symmetric, which means it is symmetric about one of its axes only, and he ended up with stresses that are not making sense to him, or is not recognized by Midas. So I'm interested to see this, but I can just verify it before I answer you on this. Okay. This because the stress is a very small unit, so we have to. Okay. Yeah, because I have to display this on part number 1, because at this stage, when we have the girder only active, it's part number 1 that's active, which is basically the girder section only. So this is the way that you can display your stress. This is at point number 1 of the section. If you switch this to point number 2, it's going to show you the stress. Of course, this section here is a perfect I section, so points 1 and 2 are the same, and they are in compression. So you can see the sign here is negative. All 4 girders are the same, which is correct because those girders are having the same length, the same applied load, so the same moment and the same section stiffness, so everything is the same. So you have to see all sections are correct. If you switch to point 3, it's going to be in tension, and point number 4 equal to it and in tension, which is the case here. So this is all coming because the moment is simply WL squared over 8 over those girders here. So I can check something like this and get back to you, Thomas, on this question, but thank you very much for the observation on this. And at this point, I think, JC, I'm done with the questions. And
all right, yeah, thank you so much, Amir. Thanks so much for your time. And I want to thank everyone for coming as well. And for all of you who asked these really good questions. I do want Amir to know that even though we limit the session to be 1 hour, we don't want to close the session after, like right on clock. But of course, if you have other commitment afterwards, you can feel free to leave. But this session is still going to be running in case there are other people who want to ask questions. But me and my colleague from Midas will stay on this call in case you have any questions. Amir, do you have anything to say?
No, I thank you very much for hosting me today, and I hope I answered the questions to the best of my ability and benefited everyone. Yeah, because I do have a commitment in 10 minutes, another meeting, online meeting, so I have to leave now, but I'll be happy to answer any questions if written or something, in case I've not covered everything today. And thank you very much for organizing those useful sessions and getting us the opportunity to talk to engineers and exchange ideas and tips together.
Yeah, thank you, Amir. Yeah, Amir, thank you again for all your time and your effort to explain this. So I want to explain again about Midas Expert Network. Amir is one of our expert engineer from Midas Expert. So if you can see my screen right now. So in this expert network, for those of you who didn't hear my presentation before, you're able to look into the webinar, go to a Q&A session like this, one-on-one consultation, conferences, getting experts, their tips and tricks of using Midas software. You can also learn a tutorial from these experts. So how do you join? And so you can just simply go to this website, midasoft.com/Midas Expert Network. So it's totally free. We do this because we want all the users and the engineers to connect with each other. And all you have to do is to fill out the form in case you feel stuck on your project, or you just simply want to have your work peer reviewed. You can feel free to just submit the form, and our team will contact you shortly. So so then now the floor is open. So you can let me know if you have any questions that you want to ask. We can try to answer them as much as we could. Yeah, Kodama, did you find the comment helpful regarding the your large deflection problem?
Yes, that's really helpful. Yeah, that the way that Mr. Amir he talked about it, the comparing during the constructions, which is the one of the solutions to work during the construction stages. So I think this is helpful, and checking the deflections using the live load, which it's checked. It's already checked my design. So this was my concern, but for the dead load, but what he answered is, I think it's the right answer for my situations. But my next check will be the fatigue and the strength. So I'm still working on these stages to see how it will work.
Right. Okay. You said you still have one more follow-up question. Is that related to the dead load, or you're following up live load?
Yeah, I mean the live load check. So my question was maybe that a little bit more in depth with my work, more than stages. But what I'm thinking, if for the checking the fatigue and the strength, I mean I just want, I mean I'm trying to see how I can go to Midas and do the design check using the design tools, and I just have some questions about, I mean, if the live load is checked, is it necessary that will be I mean will be the kind of like the possibility that make the structure will be checked in fatigue and also in the strength. I'm trying to do the next steps for checking the fatigue, but I'm not sure with this, the dead load that I have, is it gonna be also a problem with the checking the fatigue, or will be okay? I mean, this.
Angela, do you or anyone, do you have any?
So you can definitely check. I mean, since I don't really know the exact issue of your results, I think, you know, troubleshooting your death load results is the first thing. I don't really see like any reason why, you know, like anything will be an issue about fatigue analysis or design checking. So yeah, I think, I mean, regardless, you can do the fatigue design checking, but since you probably want to configure your dead load first, I think that will be the first step to it. But we can share like other references with you so you can kind of see an overview of our design checking features, strength limit state, service limit state, constructability, like fatigue, and so on.
Yeah, that would be helpful. I need some like some tutorial, maybe if there is some example how to do the design check after we do the result, like, and try to understand if they are passing the check design, for example, for AASHTO or any code analysis.
Yeah, we'll share some references. And we'll also kind of help you troubleshoot your specific model with our technical support team.
Yeah, thank you.
All right, thanks. We'll follow up. And I wonder if there anyone else who haven't asked a question and want to ask you a question, or just any comment regarding your experience, or do you want to just kind of share your project you're working on? You're welcome to.
Yes, this is Carlos. I'm the person that submitted the question about the wind.
Hi, Carlos.
Hi.
Right.
What we're trying to see is how, you know, we were looking more for like a goal to go by almost, because we had to add wind different directions during inactive and active. So, but at the same time, we don't want that wind to go for the final stage because it's a different type of wind. So that's why we wanted to just to check that wind just for during construction. So that's why we were that's what basically our question.
Right.
So Carlos, so you have to activate and inactivate like multiple different sets of wind loads, right?
Yes, it's different angles, different winds, so different stages. So.
Okay. So my question is, do you need a feature that automatically generates the wind load at different angles? Or are you talking about, like activating and inactivating different sets of wind loads in different stages? Which one do you really need? Is it the first one or the second one?
It is, I am actually inputting the wind load as a beam element, like he said, like a static load.
Right, so are you inquiring about automatic generation of the wind load, or are you inquiring about activation and inactivation?
Yes, activation and inactivation. I just want to make sure that that wind doesn't make it to the final stage.
Oh, yes, I see. Yeah, I mean, Amir kind of showed the whole construction staging. Basically, you can, if you deactivate it, that loading will not be carried throughout the next stages. So you can activate it, and like once you deactivate it, it's completely off the model, but the effect the wind load made on the structure will remain. Like, for example, any like changes on the member stresses and forces, those are going to be locked in. And obviously when the wind load is kind of unloaded again, then it's also going to make an effect. But yeah, once you deactivate it, it's not going to pass through like other stages. We'll share like more details with you at the end of the session. I think maybe just a quick demonstration wasn't like easy to remember. Like, yeah, we'll share more info.
Okay, thank you very much.
If you deactivate it, yeah, it will not go to the last stage at all. Yeah, but we'll share. Yeah.
Thank you.
All right. So yeah, thanks Carlos. So I think I just got a chat from Pankaj. So Pankaj said, can we active load on the same stage at start, then deactivate at the end time? I think Pankaj could. Do you want to talk a little bit more about what you just messaged the group? Hello, Pankaj.
I think Pankaj is talking about like if there's any way to activate a wind load and also deactivate it at the end. Basically, that's possible because for each, however, this also depends on whether you're using the time-dependent material or not. Let's just assume that you're not using, like the time-dependent material property. You're just going with simple like modular ratio, or then like the actual time input in the construction stage isn't going to be, it's not really going to matter. For example, I'm sharing my screen. For example, let's say I have this steel composite model, and I'm just using, instead of using the time-dependent creep shrinkage functions like this, that actually vary like over time. Instead of using this very like complicated like feature, let's say you're going with simpler method of using, like the modular ratio between your deck and girder, as kind of suggested by Ashto. If that's the case, then you have different material for creep shrinkage. However, that material property isn't really varying along the course of time. So what happens is, even if you really have the duration information in the construction stage analysis definition, this isn't really going to play an effect because we're not using a time-dependent function. We're just using different modular ratio that are going to be activated using the boundary conditions. So for example, if the duration, so for example, if we're using the time-dependent function materials, then yes, we can activate win load in the ones on the same stage, and we can also deactivate it on the same stage. However, if the time dependent, we're not using the time dependent material, then kind of activating and deactivating. I will double check, but my best recommendation is to activate it in the next stage.
Okay, thank you. And
yeah, if you have any additional comments, please feel free to share.
I think Pankaj just messaged me saying speaker has covered it. So yeah, I think you pretty much covered what they were asking for. So I think if there's any no more questions, we can pretty much end the session now, unless if anyone have any last minute comments or question. So if not, this session is recorded, and you can let me know if you want to have a copy of this recording just for your reference. So yeah, thank you again for everyone to come, and thank you for Amir, who has just left, and thanks for Angela, who answered some of the questions. I hope everyone have a good day. Yeah, bye-bye.